Welcome to the MOOCs course Mechanical Unit Operations. In this particular lecture, we will be discussing methods of size reduction. We have seen the requirement of the size reduction and then screen analysis, differential analysis, cumulative analysis, those kind of problems. We have seen how to find out the details of the surface area of the individual screen increment or the surface area of the entire sample or specific surface, those kind of details we have seen till now. But in order to do this size reduction, what are the methods are available, and then how much power should we provide for a given size reduction requirement. Let us say you have a kind of initial 50 mm particle size. If you wanted to reduce the size of those particle sizes to the average of 1 mm particle size, so then what are the forces are available, and then how much energy should be provided for those kind of reduction. Those things we are going to see. That is basically methods of size reduction we are going to see in this lecture, and then in the coming lecture we will be discussing the equipments available for these kind of size reduction operations. So, as already we know, the basic purpose of the size reduction is to reduce the size of the bigger size particle to the smaller size particles, because smaller size particles are very much convenient to use in any of the given unit operations or unit processes, or even for the transport or conveying as well. So, that is size reduction of solids for variety of purposes is a common requirement in many material processing industries. We will see some examples also. The reduction mechanism involves deforming of solids until they break or tear, and then how that can be done? That can be done by applying diverse type of forces, different types of forces you can do. You can apply like compaction, nut cracking kind of thing. You can apply hammering kind of forces. You can apply the filing or rubbing kind of forces. Even you can apply cutting kind of forces if you have a kind of specific size. So, different types of forces are available. So, you can apply as per your requirement of the applications. The process as per the process requirement, you can choose a kind of a force which can provide you the required size reduction, and then in general one particular force may not be sufficient to get the required size reduction. You may be applying the more than one kind of forces in general for this kind of size reduction. Those details also we are going to see sooner. For this size reduction, there is another generic term, that is comminution, right. Comminution is also a kind of generic term used for size reduction. So, objective of the comminution is to reduce the bigger particle into the smaller particles, or to produce smaller particles from larger particles. Why? Because smaller particles are having a kind of larger surface, and in this particular size reduction operations we designate these smaller particles as a kind of desired products, because it is a size reduction operation. So, whatever the reduced size particles are there, they are the products. So, in this particular module, whatever the size reduction operations have been carried out, so finally size reduced smaller particles are taken as a kind of products, whereas the initial feed whatever is there, bigger size particles we will be considering as a feed. So, we may be having two terminologies in power calculations also, power requirement for a given size reduction operation that we are going to see. So, in those cases we are going to have a two terminology, the feed and then product, feed size and product size. Okay. Feed size is the given material average size, whatever the bigger size particles their average size is a kind of feed size, and then product size is a kind of after size reduction, whatever the finer particles, smaller particles are there, so their average size is a kind of a product size. So, these two sizes are important in general in order to find out the power requirement or even efficiency of a operations. So, energy efficiency of operation can be related to new surfaces formed by size reduction. When you are doing the size reduction, so new particles, smaller particles are forming. So, that is the new surfaces are forming. So, this is a kind of indication of energy efficiency. Energy efficiency of operation now can be related to the new surfaces have been formed by size reduction. So, what are the common applications of this size reduction? Though we have seen several common and individual applications, specific applications given specified to a given problem or type of problem. So, however, we have a kind of a recapitulation again. So, common applications requiring size reduction are the crushed ore or crude ore that we crush into smaller and workable sizes, because from the natural resources what we do, we get big rocks kind of things as a kind of raw material, we crush them into the smaller sizes, because big rocks you cannot handle in any kind of unit operations or unit processes properly. Even if you handle them, the overall productivity or overall efficiency of the process will not be good enough. So what you do, you crush them into the smaller and workable size, so that you can conveniently take them into the concerned unit operations or the concerned unit processes if at all reaction is there, and then you can do the required process comfortably, or you can comfortably transport them in a kind of smaller size particles rather in a kind of bigger size particles. Then synthetic chemicals that have formed after a given reaction, so they are need to be grounded into a specified powder size. So there also after reaction some kind of synthetic chemicals formed in a solid form, they may not be in a kind of required size. So there also you need to do a kind of size reduction, so that you can have a final product in a kind of a specified powder size as per the requirement of the consumer, or as per the requirement of the subsequent process, if it is not the final product. In general, plastic sheets are cut into tiny cubes. Sometimes what happens, you need to make a kind of particles size reduction into very specific definite size and shape. You cannot have a kind of different size and shape. So you wanted to have a very specified size and shape, so accordingly you need to cut them. Sometimes this kind of cutting into the specified or definite size happens in a kind of many food processing applications, like slicing of vegetables, mincing of meat extracts, etc., those kind of applications. So like that, if you keep on listing, there are a number of applications where size reduction is kind of very much essential, as discussed now. As well, we have seen previously several applications. Sometimes this commercial requirements also is a kind of a reason for this size reduction. Sometimes what happens, commercial requirements to meet specific size and shape also makes a kind of point that you need to go for a kind of a size reduction. And then reduced size increases the reactivity of solids in general. If you have a kind of heterogeneous reaction where solid particles are reacting with given a fluid, then if your solid particle size is smaller, so then in general the reactivity of that particular heterogeneous reaction increases. Like if you take the smaller particle size, if you take bigger lumps kind of particle size, then the reactivity of solids may be very less in general. So for that reason also you need to do a kind of size reduction. Then reduction can enhance the separation of unwanted ingredients by mechanical means. Sometimes what happens, you do the separation based on the size, right? Not only for this operation, sometimes it is required to do the separation based on the size also. So when you do the size reduction, so it can be convenient to separate out unwanted ingredients from the main reactants or main products, or you can separate out the byproducts from the main products sometimes by these size reductions. In general, it may be good valid kind of thing for the reactants, where the natural ore that may be having several ingredients. So when you do the size reduction, it may be possible that some of the unwanted ingredients can be easily taken away by mechanical separations. So because of that reason also we need to go for this size reduction. Then what are the forces involved in size reduction? We know that we realize the importance of the size reductions, especially in solid operations or solid fluid operations, having seen several kind of applications, examples. So, but we need to know what are the forces that are required, or what are the forces involved in size reduction, right? So let us say you have a very big rock, and then you wanted to get a very finer particle. So if you are doing some kind of rubbing or attrition kind of thing, you may not get that required product. Even if you are getting that, you may be giving lot of energy and then lot of time to get that finer particle from bigger particle. So what you do in general, you try to break the bigger particles into the smaller ones or the mediums one, and then you further hammer those medium kind of particles, so that you can get a kind of finer particles. So like that, you have a kind of compressive forces, you have the hammering forces, you can have the attrition forces, even you have the specified kind of cutting kind of forces involved in size reductions. So those forces we need to understand first before going into the equipment and then power required for the given size reduction operation. So we list out the forces involved in size reduction now. First one is the compression, where the nutcrackers kind of action takes place. For coarse reduction of hard solids to give fines, one can apply these compressive forces. And then coarse crushing implies reduction of a sample to a size of about 3 mm. So, in general, whatever the compressive forces that you apply, from there whatever the material that you get, out of which coarse material in general have a kind of 3 mm, about to have a 3 mm size. So, that is the reason the reduction by this compressive forces is also known as a kind of a coarse reduction. Please be noted that whatever the force that we apply, whether the compression or the hammering and then attrition or the cutting kind of other subsequent forces that we are going to see, one particular force will not give only one type of a particle, that is coarse particles or medium particle or fine particles. It is possible that when you apply one particular kind of force, all three types of coarse, medium and fine particles may be possible to get as a kind of product, but depending on that, how much fraction of a given material, given product is having coarser, how much fraction of given product is having medium, how much fraction given product is having finer one. So, these forces or these reduction processes are also given as a kind of terminology as coarse reduction, medium reduction and then fine reduction. So, whatever the compressive nutcrackers are there, they are generally given a terminology or known as the coarse reduction, because when you apply these kind of forces in the product, you have a majority of the fraction coarse material. Next one is the impact or hammering kind of forces. So, here they are regarded as general purpose forces for size reduction. Here they produce again as coarse, medium and then fine, all of them they produce in general, but however, in this one majority of the fraction of the products by hammering, whatever the products of the solids you get or size reduced solids you get, out of which you have the majority of the fractions as a kind of medium fraction. So, that is the reason this impact or hammering is also known as the medium reduction, though it will also produce coarse and fines, but the majority of the fraction would be in a kind of medium size. The third type of force that is involved in size reduction is attrition or rubbing. Here this rubbing or attrition is in general applied in fine pulverization when size of product reaches micrometer range, that is when you need to have a kind of fine particle, so then you apply attrition or rubbing, right. But however, directly you cannot apply rubbing for a bigger rock size in general, as I mentioned. First you need to apply the compressive force, then reduce to those coarse material. That coarse material probably if you do hammering, and then after the hammering whatever the material is there, if you apply the attrition, so then it is possible that you get the majority of the fraction in the product will be having fine particles. So, size reduction occur from attrition of one particle by one or more other particles when they are tumbling out to each other. So, they may be going through a kind of attrition rubbing amongst themselves, and then a kind of size reduction may also take place. And then because of this reason that they produce many majority fraction fine material, this attrition or rubbing or the size reduction by attrition or rubbing is also known as the fine reduction. These are the three processes in general, right. And then despite of whatever the uniformity of the feed, the product that you get after the size reduction, you may be having the very wide distribution, you may not have the very uniform size distribution. Let us say you take a glass beads, you take glass beads of 1 centimeters size, you take several number of such glass beads of 1 centimeter, you take them in a kind of crushing equipment, and then when you apply the size reduction operation, when you crush them, you finally get the product. So, initially feed you have taken uniform feed, all the particles are having 1 centimeter size. But after crushing, whatever the product that you get, will you get the same product, or are you expecting to get the product of the uniform size? So, it is not possible. After crushing, you may be having again coarse, medium and then finer fractions, and then you have the wider distribution of the particles, right. So, that is also possible. So, that is the reason based on the dominating fraction in the product, these size reduction forces or the size reduction by different forces are given different terminology as coarse reduction. Compressive forces, when you apply you get the coarse reduction, and then if you apply the hammering forces, then you get the medium reduction. When you apply the attrition forces, you get the fine reduction. Fourth one is the cutting. Cutting is the one is applied when you need a kind of very specified size of the particles or the very specified shape, then you have to go for this cutting, and then this is in general product oriented. Product, after the reactions or whatever the process has been taken, if you pack the product in a specified size and shape, then cutting is very much essential. So, it provides definite size and shape of particles with very few fines or almost no fines. Applications we find mostly in many industries, plastics and other things, but in general food processing industries also they have plenty of applications like dicing of vegetables, slicing of fruits, mincing of meat, etc. So, by summary, what we understand, if you have a kind of compressive force, then principal action that is taking place, nutcracker kind of action, and then example of equipments where these kind of compressive forces are dominating are the crushing rolls. There are different types of size reduction equipment are available that we are going to see in next lecture probably. So, crushing roll is one of the type of size reduction equipment, in that primarily compressive force is applied, and then there is a kind of hammer mill where you applied impact kind of force where the hammering kind of action is taking place. Then we have disc attrition mill where the attrition force is applied in, and then principle of or action that is causing this reduction is the filing action. Then rotary knife cutters are there where the scissors are provided which produce the particles of definite size and shape by cutting force. Now, characteristics of comminuted products. Crushing or grinding is to produce small particles because of their large surface or their shape, size and number as well sometimes. That is the reason that we do this crushing or grinding. Crushing or grinding are some kind of size reduction operations. Okay. So, we are doing these size reduction operations to produce small particles. In mechanical separations, the energy required to create new surfaces is a measure of efficiency. So, what happens? How much power you supplied for a given size reduction operation, but how much is consumed by the particle for the creation of new surfaces by size reduction is a kind of measure of efficiency of the given process. Those things we are going to see in calculations anyway. And then as I already mentioned, irrespective of uniformity of feed, whatever the feed you have taken, it may be very uniform in size. However, after crushing or grinding kind of size reduction operations, when you apply to that feed, you may not get the uniform product, though the feed is very uniform. So, that means the product particle size distribution is very wide in general. Sometimes grinders can control the magnitude of largest particles in their product, but not the fines. Whatever the size reduction forces you apply, you get all kind of these things, coarse, medium, fine kind of thing, but you can never avoid a kind of fines by whatever the forces you apply in general, right. So, whether it is grinder or crushing, definitely there will be a kind of some kind of fines. You can control the largest size of particles, but you cannot control the smaller finer particles. Some grinders may minimize these fines. You can reduce the fines, but you cannot eliminate them. If the feed is uniform, both physical and chemical structure, then shapes of individual units in the product may be quite uniform. Let us say the microstructure of the particles in general having a role in size reduction. When you take a material and do the size reduction, so whatever the particles that you are going to get, their shape primarily have a kind of some resemblance with their microstructure. Let us say galena always produces, if you take a big lumps of galena and then do the size reduction, you primarily get a particles of cubical shape, not exactly cubical, but resemblance to the cubical shape you can have. So, that is because of the microstructure of the galena. As I already mentioned, whatever the size reduction you do, compression, hammering or attrition, the particle size distribution is going to be very wide, irrespective of the uniformity of the feed. The product, the size reduced material is going to have a very wide distribution of the size. So, that is the ratio between the largest size particle and then smallest particle of the product is in general of the order of 10 power plus 4. Such wide is the product size distribution for the product obtained after this size reduction. Then after crushing, unless the particles are smoothed by abrasion, comminuted particles resemble to polyhedrons with nearly plane faces and sharp edges and corners. These polyhedrons in general may have 4 to 7 faces depending on the type of material that has been crushed. So, if you have more number of faces, then sometimes they can also by abrasion while the process they go through the abrasion and they become spherical shape. Otherwise, in general the polyhedrons will have 4 to 7 faces. They may be compact with length, breadth and weight almost nearly equal. However, they also be kind of plate like or needle like shape also. So, having seen the size reduction requirements and then their general characteristics, now we see the energy requirements for a given size reduction operation. So, energy and power requirements in comminution. Major expense in crushing and grinding is the power cost. We have variety of equipments. Let us say we have a ball mill. Ball mill is a kind of size reduction equipment. Details we will be studying later again. In this ball mill, usually you have a cylindrical container. In that cylindrical container, you have a very big size iron balls, metal balls like 10 centimeters, 5 centimeters. There may be some balls of 1 centimeters. Those balls are kept inside the container. In that cylindrical container having these balls, metal or heavy balls, we pour the solid material which we need to do the size reduction, and then we rotate the cylinder. When we rotate the cylinders, whatever the balls are there, metal balls are there inside, they will also be lifted up, and then when they go to the top surface of the cylinder, because of the gravity they fall down. Alright. So, when they fall down, they show some kind of force on the solid particles, and those solid particles break depending on their ultimate strength. Alright. So, this is how the size reduction takes place. Now, you need to provide the power for rotating these cylinders, and then power for lifting these particles and all those things, and then power for bearings and fittings, etc., to avoid the friction between bearings and fittings, etc. These many, this in the equipment you have to provide the power for those many kind of things, but only fraction of power is utilized by the particles for size reduction. Whatever the power required to lift the ball up, metal balls up, and then they are falling down because of the gravity. Right, only that much fraction in general is a kind of utilized by the particle for size reduction. All other power that is given, that is for operation only, not for the size reduction of the given operations. Like that, you can see many other equipments also. There are heavy kind of parts which need more power for operating than required for the original size reduction. Okay. So, that is the reason major expense in crushing and grinding is the power cost, and then that is the reason factors that control power cost are very much important. So, one has to find out what are the forces that are controlling the power cost, and accordingly one has to tune the parameters so that the power expenses can be reduced. Then during size reduction, the particles of feed material are first distorted and strained. Work necessary to strain the particles is temporarily stored in the solids as mechanical energy of stress. Then additional force is applied to the stressed particles so that they distorted beyond their ultimate strength and suddenly rupture into fragments and new surfaces are generated. This is the mechanism in general how the size reduction is taking place. The particles of material are first distorted and strained. Whatever the work necessary to strain the particles, that is stored as temporarily in the solids as mechanical energy of stress. Then additional force when you apply to the stressed particle, they distorted beyond their ultimate strength, and then suddenly they ruptured into the fragments, into the smaller particles, and new surfaces are generated. This is the mechanism in general size reduction takes place. However, since unit area of solid has a definite amount of surface energy, the creation of new surfaces requires work, and then that is a kind of a measure of efficiency of the process. This work is supplied by release of energy of stress when the particles break, and then by conservation of energy, all energy of stress in excess of the new surface energy created must appear as heat. So, whatever the energy that we or the power we supply for the operating of this equipment and all that, all that energy is not being consumed by the particles so that they break. Only a fraction of that energy is being utilized for the solid reduction or the reduction of the solid particles, but rest everything is not utilized. It is only for the operating, so that has to be dissipated, and that usually dissipated as heat. So, that is the reason many of the size reduction operations during the operation or end of the operation, if one touches the surface of the equipment, one can clearly feel the temperature is very much higher, the equipment becoming very hot. Efficiency. Size reduction is one of the least energy efficient of all the unit operations. Why? Because as I mentioned, for a given example of ball mill I have taken that example, if you see only small fraction of power that is supplied is utilized by the particles for the size reduction, rest all for operating of the equipment and all that. Right. So, that is the reason the size reduction operation is one of the least energy efficient operations among the all unit operations of chemical engineering. And then you will be surprised to know studies revealed that only less than 2% of the energy applied to the solids is used to create the new surface. Whatever the, let us say you giving 100 kilowatt power for the required size reduction. So, only probably 2 or less than 2 kilowatts are being utilized for the size reduction, rest everything is for the operating of the equipment and then overcoming the friction between bearings and all those things. So, all that energy, rest energy is going into that one. So, that is the reason this is a kind of very least energy efficient process. Whatever the remaining energy is there, that is dissipated as heat. In operating size reduction machines, energy must also be supplied to overcome friction in the bearings and then moving parts, as I already mentioned. And then mechanical efficiency is the ratio of the energy delivered to the solids to the total energy input to the machine. So, since we already seen that only fraction of energy is being utilized by the solids for a given size reduction operation. So, that utilized energy divided by the total energy supplied to the size reduction equipment, that will give a kind of a measure of mechanical efficiency. So, mechanical efficiency is the ratio of the energy delivered to the solids which are being reduced to form a new surface divided by the total energy input to the machines. The ratio of the energy delivered to the solids to the total energy into the machines, that is the mechanical efficiency. And then this efficiency in general is very small, in between 25 to 60%. So, having seen the energy requirements, what we see now, we try to see the available crushing loss and work index. So, like crushing loss in the sense, they will give a kind of a priori information how much power one should supply for size reduction per unit kg of the feed, right. So, let us say initially feed you are having 50 mm particle sizes, and then you are reducing them by size reduction, so that you get 1 mm particle size in general. So, that from 50 mm particle size to 1 mm average particle size, if you wanted to convert for a given equipment, how much power is required per kg of the feed, per kg of the sample that you have taken. So, that a priori information one can get by this crushing loss, and then this crushing loss, there are different types of crushing loss are there. We take only a few of them which are found to be reliable. Various laws and theories are proposed for predicting power requirements for size reduction of solids, and unfortunately they do not apply well in practice. You apply this crushing loss and then you have a kind of a priori information how much power requirement for a given size reduction operation, but according to those calculation, if you go and try to implement in a kind of real life situations, you may end up that you may not be getting the same thing. So, that means this crushing loss are a kind of indication how much power is required, but they cannot give a kind of accurate number, the relatively accurate number of the power that is required for size reduction. So, that is not possible because of this some limitation that we are going to see anyway. So, approximate calculations give actual efficiency of about 0.1 to 2% only. By using these things, whatever the crushing loss you use and then you do the approximate calculations, you get actual efficiency of 0.1 to 2% only. So, let us say actual efficiency is something, but when you apply these things you may get only 0.1 to 2% of that efficiency, you may not get the actual efficiency. So, this is the other drawback. However, it serves some kind of basis for selection of power, how much power should be given kind of thing. In deriving these crushing laws, there are kind of assumption, but there is a one common assumption. What is that assumption is the energy required to produce a small change dP in the size of unit mass of material is a power function of the size of the material dP. Let us say initially you have a dP size, particle size, average size of the particles is dP. You wanted to reduce its size by small change dP. To bring that small change in the size of the initial particle size dP, how much power is required per unit mass, right? That power requirement per unit mass is proportional to or is a kind of power function of this particle size, that is dP by dDP is proportional to 1 by dP power n. This is a kind of generalized assumption. If you take n is equals to 2, you may get one law. If you take n is equals to 1, you may get another law. If you can take n is equals to 3 by 2, you may get another crushing law. So, different crushing laws are generalized by this particular assumption. So, here dP is particle size which is in mm, P is power requirement in kilowatts, and then m dot is a kind of mass flow rate which is in tons per hour. So, now we take one by one each of these crushing laws, right. First we take n is equals to 2. If you take n is equals to 2 in this equation, dP by dDP proportional to 1 by dP power n. Here if you take n is equals to 2 and then do the integration and then substitute the limits of feed size to the product size, then you will get P by m dot is equals to some constant multiplied by 1 by dPb minus 1 by dPa. That constant is known as the Rittinger's law constant. If n is equals to 2, if you substitute n is equals to 2 in this particular equation, whatever the crushing law that you get, that is known as the Rittinger's law, and then after integration substitute the limits. So, you will get that constant Kr, that Kr is known as the Rittinger's constant, and it is dimensional quantity. It is not dimensionless, it is having some dimension. And then here dPb is the average size of the particle in the product, that is after the size reduction, whatever the product that you take, that you get, the average size of that product is dPb, and then dPa is the average size of the feed. Before crushing, whatever the feed that you have taken, the average size of that particular feed is dPa, okay. And then m dot is the mass rate of the feed, and then P is the power requirement for this size reduction to reduce the size of the particle from dPa to dPb. So, this is for the feed size, this is for the product size. Now, this equation, as long as 1 by dPb minus 1 by dPa remains same, the power requirement is going to be same. That is what you can understand from this equation, because for a given material and for a given equipment, Kr is a constant, right. So, as long as this 1 by dPb minus 1 by dPa is remains same, you will get the same power requirement. So, but that is not true. That is not true. That is, let us say if you have a kind of average size of the feed material is 100 mm, you are doing some size reduction, then you get the product having the average size of the particle is 50 mm. So, 1 by 50 minus 1 by 100, you get 1 by 100, right. So, whatever the power that you required for that case, let us say some x kilowatts, right. Then you take a feed 50 mm and then product that you get, let us say if you are expecting to have 33.3 mm product size, average size of the product you want 33.3 mm. Then again 1 by 33.3 minus 1 by 50 is again 1 by 100, close to 1 by 100. So, that means in this case also the power requirement would be same, but in practical that is not going to be true. That is the reason, as I mentioned, these crushing laws are do not hold well with the practical situation, but they give a kind of a priori information. So that is not going to true. So that indirectly you are saying that 100 mm particle size you take and then crush them to get a 50 mm size particle sizes, whatever the power requirement is there, the same power will be required if you wanted to reduce that 50 mm size particles to further smaller 33.3 mm size particles. So that is not going to be true in general. Okay, that is one of the limitations. This limitation is there for other laws also. And this law has been found to hold better for fine grinding, where a large increase in surface results. Okay. So wherever you have the fine grinding, it is better to use the Rittinger's law in general, so that to have a better reliability. So these things are one finds from the experience of different equipments and different types of materials. So in general, if you are doing the fine grinding, then power requirement calculation for that fine grinding if you need to do, so it is better to use the Rittinger's law. Now we take example problem before going to the next crushing law. So a material is crushed in a kind of crusher. The feed size is 50 mm and then you are expected to have a product average size 10 mm. So for this case, the power energy consumption is 13 kilowatt per kg per second. So kilowatt is power, kg per second is a kind of mass rate. So that means P by m dot is given. Feed size is given, product size is given, and then P by m dot is given. So from this information one can find out what is the constant, what is the proportionality Kr constant, Rittinger's constant, that you can find out. Then what would be the consumption of energy needed to crush the same material of average size? Now if the feed becomes bigger, if you are next time handling bigger size feed 75 mm and then you are trying to get 25 mm product average size, then how much power is required if you apply the Rittinger's law? So it is very simple. First case, the feed dPA is 50 mm, the product dPb is 10 mm. The average size of the feed is 50 mm, the average size of the product is 10 mm. Now you apply the Rittinger's law. P by m dot is equals to Kr multiplied by 1 by dPb minus 1 by dPa. P by m dot is given 13 kilowatts per kg per second. Okay, Kr, and then dPb is 10, dPa is 50. So here you get Kr is equals to 162.5 kilowatt per kg mm. Now in the second case, if the feed average size becomes 75 mm and then you are expected to get the product average size 25 mm, how much power is required? That is how much P by m dot required, that you need to calculate, because m dot is not given. So now use the same equation. Kr just now you calculated as 162.5. In this case dPb is 25, second case, and then feed in the second case is 75 mm. So that you substitute here, then you get P by m dot is equals to 4.33 kilojoules per kg. This is the power requirement if you apply the Rittinger's law. So let us remember this value, because the same problem using the same values we are going to do for by applying the other law, and then we can compare the power requirements. Are they giving the same power requirement or not? Right. So by Rittinger's law, for this problem we are getting power requirement 4.33 kilojoules per kg. Okay. Next, Kick's law. If you substitute in this dP by ddP proportional to 1 by dP power n, you substitute n is equals to 1, then integrate and then substitute the limits of dPa and dPb, that is the feed average size to average particle product size, then you will get this Kick's law by substituting n is equals to 1. So that comes out to be P by m dot is equals to some proportionality constant Kk ln dPa by dPb. This Kk is known as the Kick's law constant. It is again dimensional quantity. It is not a dimensionless quantity, it is also having dimensions. And then same as the previous case, dPa is the feed average size and then dPb is product average size. Now here also what we understand, as long as the dPa by dPb ratio remains same, so the power requirement is going to be same. Let us say dPa 100, dPb is 50, so 100 by 50 2. So, whatever the power required for reducing the size of feed 100 mm to get product 50 mm, then whatever the power requirement is there, that is that going to be same for the feed 50 mm and then getting product 25 mm, because 50 by 25 is again 2. But that is in general not true. That is the reason this kind of restrictions is there here also. That is, this law applies that the same energy required to produce a material from 100 mm to 50 mm as is required to reduce the same material from 50 mm to 25 mm, because 100 by 50 is 2, 50 by 25 is again 2. So, according to this law, as long as dPa by dPb ratio remains same for a given material being crushed in a given equipment, that power requirement is going to be same, but in reality that is not true in general. This law has been found to hold more accurately for coarser crushing, that is when you use the compressive forces etc. or coarse reduction when you do. So, Kick's law found to be reliable, whereas the Rittinger's law is found to be very much reliable if you are doing fine grinding, fine reduction. Now, the same example problem whatever we have taken in the Rittinger's law case, now we apply Kick's law. That is, initial feed size is 50 mm and then 10 mm is the product average size, 30 kilowatt per kg per second power requirement is there. And then in the second case, if the feed becomes slightly bigger 75 mm and then product becomes 25 mm, how much power is required? These numbers, feed and product sizes and then power requirement in the first case exactly same. So, second case, whatever the power requirement, is it going to be same as in the Rittinger's law or not? That is what we are going to see. So, Kick's law, if you apply, first case dPa is 50 mm, the product dPa 50 mm, the feed size, the product size dPb is 10 mm. When you apply the Kick's law, P by m dot is equals to Kk ln dPa by dPb. So, P by m dot is given as 13, dPa is 50, dPb is 10. So, Kk you get 8.08 kilowatt per kg per second. Now, second case, feed is dPa 75 mm, average size of the feed is 75 mm and then average size of the product is 25 mm. So, then how much power is required? We apply the same equation, P by m dot is equals to Kk ln dPa by dPb. Kk we just now found it as 8.08, that you can substitute here, but now dPa is 75 and dPb is 25. So, then you will get 8.88 kilojoules per kg. But we have seen Rittinger's law just now in the previous case, same problem. What we have obtained? We obtained P by m dot is 4.33 kilojoules per kg. So, now you can see by using different types of laws you get the different power requirements. So, you need to have a kind of experience in what case what kind of crushing law should you use. So, what we have seen, if you are doing the fine reduction, so Rittinger's law is a better option. If you are doing the coarse reduction, then Kick's law is a better one, or the numbers, power requirement numbers given by Kick's law under coarse reduction is more reliable, and then power requirements given by Rittinger's law for size reduction is more reliable. In this case, both product and feed are bigger size, in 50 mm, 10 mm like that. So, they come under coarse size reduction. So, for this problem, whatever the numbers that you get by Kick's law, that is going to be more reliable. So, that comes with the experience of doing several operations and then finding out. So, people have found that for coarse reduction, the power requirement obtained by Kick's law is more reliable. So, that is, this number is going to be more reliable than this number, because Rittinger's law is good for the fine reduction, not for the coarse reduction, whereas the size in this problem is a kind of in the coarse reduction size. So, this is going to be more reliable, 8.88 kilojoule per kg is going to be more reliable. So, next before going to the next law, we will take an example problem on Kick's law. So, here a crusher is fed with limestone having particles 2 centimeters median equivalent diameter. What do you mean by median equivalent diameter? that means 50% of if the median equivalent diameter is dm. So, that means 50% of material would be having size less than dm, and then 50% of the material would be having more than dm size. Then the dm is known as the median equivalent diameter of the sample. So, here in the sample 2 centimeter is the median equivalent diameter, that means the 50% of the material in the sample is having less than 2 centimeter size, and then 50% of the sample is having more than 2 centimeters. So, feed is 2 centimeter size, discharge product is having 0.5 centimeter median equivalent size. The capacity, the flow rate is mass rate is 1.2 into 10 power 4 kg per hour, and then under such condition it is consuming 7.46 kilowatt of power if the requirements of the process demand a finer size of the product. Now, the feed is same, but the product, if you wanted to further make it fine to 0.4 centimeter of median equivalent diameter, by decreasing the capacity 1.0 into 10 power 4 kg per hour, then how much power would be required. So, now the product, in the second case, product size is reduced as well as the capacity is also reduced. So, by doing that way, by changing these operating conditions requirement as well as the operating conditions, flow mass rate conditions, the power requirement, is it going to change or is it going to be same? That is what we are going to calculate. So, in the first case, first of all, the problem, it is not given which law should be used, since the size of the feed as well as the product in the centimeter cases, what we can say, it is going to be in cost reduction category. So, for cost reduction category, we have seen that Kick's law is a kind of better options compared to the Rittinger's law. So, we are going to use here Kick's law. First case, dPi is 2 centimeter, the feed size is 2 centimeter, product size is 0.5 centimeters. So, P by m dot is equals to Kk ln dPa by dPb. P by m dot we substitute here, Kk we do not know, dPa is 2 centimeters and dPb is 0.5 centimeters. So, from here what we get, Kk as 4.48 into 10 power minus 4 kilowatt hour per kg. You can see this is dimensional quantity as I mentioned, it is not dimensionless. But now in the second case, feed is again remaining same 2 centimeters median equivalent size, but product is 0.4 size. The product is becoming slightly finer, and then capacity is decreased to 1 into 10 power 4 kg per hour. Then we apply the same law, what we have, P by m dot is equals to Kk ln dPa by dPb, m we can take to the right hand side. So, then P is equals to Kk is 4.48 into 10 power minus 4 as just seen, and then m dot second case is reduced to 1 into 10 power plus 4, and then ln dPa is 2 centimeters, dPb is 0.4 centimeters. So, the power requirement is going to be 7.21 kilowatt. So, from this conclusion what we understand for this problem, not generalized one, specific to this problem, when you reduce the or when you make the product slightly finer, at the same time if you reduce the capacity of the equipment, whatever the mass rate, if you slightly reduce, the power requirement is not going to be affect much, because in the first case 7.46, in the second case 7.21 kilowatts, similar kind of thing. Okay. But this is specific to this problem, we cannot generalize this conclusion for all kind of situations. Next one is the Bond's law. There are two different ways of doing it. Let us say if you have dP by d dP proportional to 1 by dP power n, if you take n is equals to 3 by 2 here and then do simplifications, you get the Bond's law. That is one way. Other way is that you can find the other ways also that we are going to see. So, it has been found that this Bond's law is a kind of more realistic way of estimating power required for crushing and then grinding of material, because this law postulates that work required to form particles of size dP from a very large feed is proportional to the square root of the surface to volume ratio of the product. So, whatever the power requirement is there, that is proportional to the square root of Sp by Vp of the product. So, that is P by m dot is proportional to the square root of Sp by Vp of the product that is going to form. And then we have seen previously this Sp by Vp, we can write it as 6 by pi s dp, dp is the nominal size of the product now. So, from here if you take out the proportionality and then whatever the proportionality constant combined with 6 pi s etc., all those things, you can write this equation as P by m dot is equals to Kb by square root of dp. Kb is Bond's constant, and then it is function of the type of machine used for a reduction and then as well as the type of the material that is being crushed. Okay. So, this is the Bond's law, but we are going to use it in the same Bond's law in a different form, right. For that we need to define a kind of work index. Work index is defined as the gross energy requirement in kilowatt hour per ton of feed needed to reduce a very large feed to such a size that 80% of the product passes 100 micron screen. So, this work index Wi is defined as is nothing but P by m dot for a case where the large material, large size particles crushed such a way that 80% of the product should pass through 100 micron screen. So, that is dp is going to be 100 microns. So, whatever the P by m dot is there, that is Kb by square root of dp. So, here now dp if you take 100 microns, in this law actually we have already seen that P is in a kind of previous case kilowatts and then dp is in mm, it has to be taken in mm. So, then what you get, Kb is equals to square root of dp is nothing but 100 microns, that is 100 into 10 power minus 3 mm P by m dot. So, this square root of 100 multiplied by 10 power minus 3, this value is going to be 0.3162. So, 0.3162 and then P by m dot is nothing but Wi. This Wi is a kind of work index. So, here in this equations whatever the dp that we have taken, that should be in mm, and then power should be in kilowatts, and then m dot, the mass rate should be in tons per hour. So, that is work index. How you define? This is going to be very important Bond's law, because when you need to do analysis, power size calculation, sometimes this dpa, dpb sizes are not given. They may be given in kind of a screen analysis, something like that. So, you have to find out what is dpa, dpb from the screen analysis data. That is also becomes essential sometimes. So, how to find out? You have to select a size through which 80% is passing through as a kind of required size if it is a feed. If it is a product, similarly what is the size 80% of the product is passing through, that should be taken as the average size of the product size. We are going to see the problem anyway. So, that is the reason the definition of this work index is kind of very important in understanding and solving the problems. So, work index is defined as the gross energy requirement in kilowatt hour per ton of feed needed to reduce a very large feed to such a size that 80% of the product passes a 100 micron screens. If 80% of the feed passes a mesh size dpa and then 80% of the product passes a mesh size dpb, so then dpa should be feed size and then dpb should be product size. So, this is how you need to find out if dpa, dpb is not given, right. Because for that Bond's law it is required that when you use the work index, so then 80% concept should come out, that 80% of the material passing through whichever size is there, that should be taken as a kind of size required size for the calculations. Then if you write in terms of both feed and product form, the feed size and product size. So, then the same Bond's law we can write now, then P by m dot is equals to Kb, just now we have seen 0.3162 Wi. So, and then this remaining 1 by square root of dpb minus 1 by square root of dpa that you get. So, this is the other form of the Bond's law when you are taking the reference of two sizes, feed size as well as the product size. So, P by m dot is equals to 0.3162 Wi multiplied by 1 by square root of dpb minus 1 by square root of dpa. This Wi work index includes the friction in the crusher, and then power achieved by this above equation is the gross power which includes the friction etc. the value of Wi is available for many standard solid materials, both wet grinding and dry crushing, such as bauxite material, coal, coke, cement clinker, clay, granite, limestone, etc. For several materials, this Wi information is available. As we have seen that Kb is function of the equipment used and then what type of material have been crushed. So is the Wi also, because Wi is related to Kb directly. So that is the reason Wi is function of again the equipment used for the crushing as well as the material that has been used for the crushing and then material that has been crushed. So for both wet grinding and dry crushing, for the several kind of materials, this Wi information is available. And then fortunately this Bond's law holds reasonably well for variety of materials undergoing coarse, medium and fine reduction. Unlike the other two laws where Rittinger's law is holds good only for fine reduction and then Kick's law holds good only for coarse reduction, but Bond's law holds good for all three types of reductions, coarse, medium and fine reductions. We will see some numbers of Wi for dry crushing and grinding. For different types of materials, these Wi numbers are given here. They are given for wet grinding. So, whatever the materials given here, that is given for the wet grinding. If you are doing the dry grinding, so these numbers, whatever the Wi numbers given in these tables, they should be multiplied by 4/3. In the table, whatever the Wi numbers are given for the wet reduction, size reduction. If you are doing the dry size reduction by dry grinding, then these numbers should be multiplied by 4/3. Now we take an example problem so that we can understand how to apply this Bond's law for a power requirement for a given size reduction operation. So calculate power required to crush 100 tons per hour of limestone if 80% of feed passes a 2-inch screen and 80% of the product passes 1/8 inch screen. So it is clearly given that 80% of feed is passing 2 screens. So that means dPa is nothing but 2-inch screen. So dPa is nothing but 2 inch and then dPb is nothing but 1/8 inch, because product 80% of the product passes through 1/8 inch screen. So this dPa is nothing but 2 inches that you have to convert into mm, and dPb is nothing but 1/8 inches that you have to convert into mm as per the requirement of the problem. So m dot is given 100 ton per hour. So we need m dot in tons per hour. So that is as it is. dPa is 2 inches. So you convert into the mm. dPb is 1/8 inches, that also you convert into the mm. Then we have P by m dot is equals to 0.3162 Wi multiplied by 1 by square root of dPb minus 1 by square root of dPa. And then from the tables we can understand the limestone, for limestone Wi is nothing but 12.74. So you substitute dPb, dPa, m and Wi here in this equation. So you will get power requirement as 169.6 kilowatts. Okay. So compared to the previous laws, what is the additional thing that we need to give attention here? What is the dPa size, dPb size? You have to take based on the 80% of material passing through which screen, that you have to take as the size of that particular sample, whether it is feed or product. So here 80% of feed is passing through 2-inch screen, that is the reason dPa is 2 inches. Similarly 80% of the product is passing through 1/8 inch screen, that is the reason here dPb is 1/8 inches. Okay. So now we take one more example problem so that we can understand clearly here. So 2 kilowatt has to be supplied to a machine crushing a material at the rate of 0.3 kg per second from 12.5 mm cubes to a product having 80% of the product having 3.175 mm, 10% of the product is having 2.5 mm size and then remaining 10% is having 2.25 mm size. So product size distribution is given, 3 sizes it is given, 80% is having 3.175. So dPb is 3.175. The distribution is based on the mass basis. What would be the power which would have to be supplied to this machine to crush 0.3 kg per second of the same material from 7.5 mm cube to 2 mm cube. So, in the first case all the details are given. So, in the second case power details you need to find out. Okay. So, in the first case P is 2 kilowatt and then mass rate is 0.3 kg per second, you have to convert it into tons per hour. dPa is 12.5 mm, it is given. Product is having 80% of 3.175 mm size material. In the product 3 values are given. Some material is having 80% material having 3.175 mm and then 10% of material is having 2.5 mm and then remaining 10% of material having 2.25 mm. So, which one should be taken? So, as per the Bond's law, whatever the 80% of material passing through the screen size, that size should be taken a product as a kind of size, required size. So, in the product 80% of the material is having 3.175 mm size. So, that means dPb is 3.175, one has to take. You cannot take 2.5 mm or 2.225 mm of remaining 10% material. Okay. So, according to Bond's law, we can say now dPb is 3.175 mm. This is the only difference compared to the other crushing laws. One should be careful in applying these things. So, now m dot 0.3 kg per second, so that you convert into tons per hour and then P should be in kilowatts, that is anyway given. So, Bond's law P by m dot is equals to 0.3162 Wi multiplied by 1 by square root of dPb minus 1 by square root of dPa. So, you substitute all the values here, the P is given here, m dot is given, Wi is not known, dPa is 12.5, dPb is 3.175. You do the simplification, you get some number for Wi, work index. So, from the first case of the data we find out the Wi. Now, in the second case, if dPa becomes 7.5 mm and dPb becomes 2.5 mm, how much power required, that is you need to find out. So, here in the second case P by m dot is same and then is equals to 0.3162, Wi just now we calculated, so that you can substitute here, dPb is 2 mm, dPa is 7.5 mm. So, here in this equation everything is known except P, Wi is also known because just now we calculated this Wi, that you can substitute here. So, you get P as 2.4612 kilowatts. Now, we take a last example problem where we can understand the things much better. So, here a trap rack is crushed in a gyratory crusher, the feed nearly uniform 2 inches spheres. The differential screen analysis of the product is given by first grind 1 in table 1. In the next slide we will see, by reducing the clearance between the crushing head and the cone. In this gyratory crushers we can reduce the clearance between the crushing head and the cone. So, that clearance is reduced and then again the crushing has been done. So, whatever the differential screen analysis of the product that we get by reducing the clearance between the head and cone of the gyratory crusher, that is labeled as grind 2. So, in the same material, same equipment 2 times grinding has been done. Initially whatever the clearance between the crushing head and then cone was there, that is reduced in the second case, that is the only thing, that space is reduced. Actually gyratory crusher, that equipment we are having something like this. So, this is the crushing head and then this is a kind of cone. So, whatever this clearance that you can adjust. So, in the second case the clearance is reduced. So, that after reducing the clearance, whatever the product you get and then do the size analysis, its differential screening analysis is given as a grind 2 in the table 1. So, using the Bond method, estimate the work necessary per ton of the work in both the first and second grinds. The work index is given as 19.32. The screen opening information is given in table 2. So, table 1, this is actually mesh size, first grind, second grind is given. Similarly, mesh size, first grind, second grind is given. Actually 4 by 6, 6 by 8, 8 by 10, 10 by 14, 14 by 20, 20 by 18, 28 by 35, 35 by 48, 48 by 65 minus 65, 65 by 100, 100 by 150 minus 150. In the first grinding, only up to 65 mesh size only it is having, because there are not much finers. So, in the second grinding the more finers are there, so further more screens are attached at the bottom. So, this first grinding 3.1 is nothing but that is mass basis. So, 3.1% of the mass solid mass is retained on 4 mesh. 6 by 18 10.3, that means 10.3% of solid mass fraction percentage of the solids is retained on mesh 6. Like that all the information, the mass fractions are given here for both first and second grind, right. So, that is given here. So, you need to know the size of mesh 4 and 6 like 8 and 10 and all these meshes, the sizes are need to be known. So, mesh 4, 6, 8, 10, 14, 20, 28, 35, 48, 65, 100, 150. Their mesh openings DPI in mm's are also given here in the table. So, this is table 1, where it is giving the differential analysis for the first grind and second grind. This is table 2, where it is giving information about the mesh opening of all the screen increments that have been used for differential analysis. Whatever the differential analysis process that we have seen previously, that data is given here. From here we are going to calculate the power requirement. So, the same thing we are going to tabulate it. The mesh size, so average size of 4 by 6 is nothing but the average of the 4.699 plus 3.327 divided by 2, that comes out to be 4.013. Like that average dia for all the these things are given here, calculated and provided here. So, in the table first grind, second grind, whatever the fractions are given, that is the material retained, their percentage of material retained is given, because that is how the differential analysis that we know. 4 by 6 corresponding xi is 3.1, xi percent is 3.1, that means 3.1 percentage of material is retained on the screen 6, passing through 4 and then retaining on 6, like that, passing through 6 retaining on 4, like that. So, like that all these things are there. So, you need to find out how much material has passed through. Overall is 100%. So, from 100 if you subtract 3.1, that means 96.9% of the material is passed through screen 4. Only 3.1 is retained, 3.1 percentage is retained on screen 4 and 96.4% is passed through screen 4 or mesh 4. Similarly, in the second case 10.3, that means this whatever the 3.1 plus 10.3, that material, that amount of material is retained up to 4 and 6 screens, and then rest all material is passed through, that is 100 minus 3.1 minus 10.3, that is 86.6% of material has passed through screens mesh 6, like that. Similarly, here in the case 100 minus 3.1 minus 10.3 minus 20, that is 66.6% of material that is passed through screen 8, that is passed through screen 8. Like that one can construct for all the screens how much percentage of material passed through for a given mesh increment. Similarly, one can do the same thing for the second grind here also. In the first grind, no material is retained on size mesh 4, that means all the material is passed through mesh 4, 100 minus 0, 100. Next case, only 3.3 is retained on 6 mesh, that means 100 minus 3.3, that is 96.7% of material is passing through the 6 mesh. Similarly, next case 8.2 is only being retained on 8 mesh, that means 100 minus this 3.3 minus 8.2 are the amount that is passed through, that is 88.5% is passing through the 8 mesh. Like that here 77.3, that is 100 minus 3.3 minus 8.2 minus 11.2, that is 77.3% of material is passing through 8 mesh. Why we are doing this passed through kind of things? Because from here only we get the respective numbers, how much 80% of the material passing through, that size we have to take a reference size for the product. Feet size is given, that is the reason we are making this the tabular column passed through column as well in addition to the given retained column. So, that means in the first grain, so 80% is between these two, right, 6 by 8 and 8 by 10. So, in between these two somewhere it is having 80% of material passed through. So, you can do the graphical method material passed through versus the average size DPI, and then you have the curve for this passed through versus average size. So, 80 corresponding to 80%, whatever the DPI is that you are getting, that DPI you should be taken as a DPB for the first grind. Similarly, for the second grind also, the material passed through fraction versus DPI you plot, and then corresponding to 80% whatever the DPI is there, that should be taken as DPB for the second grind. So, we are not going to do the I mean you can do the interpolation also, we are not going to do the graphical methodology. Similarly, here in the second case, in between these 88.5 and 77.3, somewhere 80% is passing through, corresponding DPI, average DPI we should take as a kind of product DPB. So, that is somewhere in this one. So, for the first case, DPB would be somewhere between 2.8445 and 2.0065, and then for the second case DPB would be somewhere between 2.0065 and 1.4095. So, those things only we are going to find out and simply substituting in the Bond's law, rest everything is known. DPB should be found either graphically or by interpolation. For the first grain, I am doing the linear interpolation assuming there is no much deviation. So, DPB when you do the interpolation for the first grain, you will get 2.56796 mm, and DPA is given as 2 inches, WI is given. So, once DPB is known, everything is known in this Bond's law except the P by m dot. So, that P by m dot you can find out. So, WI is also given as 19.32. This is DPB just now you find out, and DPA it is given feed in the problem. So, P by m dot you are going to get this one. So, exactly the same thing for the second one we have to, second grind we have to do. For the second grind, if you do the interpolation DPB, you are going to find it out as 1.5534 mm. So, that you substitute here in DP in this equation. DPA, WI, rest everything, and m dot, all these things are remaining same. So, you can find out P. So, m dot is not given. So, P by m dot you can find it out for this case also as 4.044 kilowatt hour per ton. So, that means in the first case the power requirement in the first grind, power requirement is less, close to 3 kilowatt hour per ton, whereas in the second case where by reducing the clearance between the crushing head and the cone, you are getting more fines. So, in such case you need to provide more power. So, almost 4 kilowatt hour per ton. Previous case in the first grind it is almost close to 3 kilowatt hour per ton. Now, here by reducing the clearance between the crushing head and then cone, whatever the operation you do, you get you need more power to be given, that is 4 kilowatt hour per ton, and then you are going to get a more finer product. So, this is how problems we have to solve using this crushing laws in order to get the power requirement for a given size reduction operations. These are the reference books that I have followed for this particular lecture. The problems that I have discussed may be seen in these first 3 reference books, exercise as well as the solved examples you can find from these examples. Some of them have been taken here in this particular lecture. Thank you.